All right. So last time we had just stopped at discussing polarity of bonds, right? So what do you mean by polarity of bonds? Like, what do you understand by the term here? How much of magnetism did you guys do till grade 10? Like, what do you know about magnets or magnetism as such?
In 10th, we did electromagnets.
Okay.
Yeah, we covered electromagnets, types of magnets, how
Mm-hmm.
it affects, how magnetic fields affect, like how stuff gets affected in magnetic fields. I think that's it.
Okay. All right. So you guys are aware of like poles of the magnet, polarity of magnet, the dipole. What do you
Yeah.
mean by dipole and all that? Okay. All right. Now, when we're talking about polarity of bonds, right? Now, this polarity of bonds is like we talk about it exclusively in the case of covalent bonds alone. Uh, Ionic bonds may polarity of bonds does not make sense. Any guesses why?
Because they get neutralized.
Mm, no. I mean, like the two charges definitely don't get neutralized. Like you still have cations and anions. But why do we not talk about polarity of the bonds there in that case?
Because you know that it's going to be a cation and an ion. It's definitely going to attract each other.
Mm. Yeah, so there is complete separation of charges in the ionic bonds. That is the reason why. Like you have a purely positive charge and a purely negative charge that are like basically attracted to each other, and that's how the lattice is formed. Uh, in covalent bonds, now because electrons are being shared between two atoms, there is going to be some amount of polarity between the two atoms. Let's see where this polarity is coming from. Huh? Another main thing about polarity of bonds is that you will see this exclusively in heteronuclear molecules. What do you mean by heteronuclear molecules? So it's given right here. So a molecule formed by two different atoms. So hetero is different. Okay. So when you have two different atoms, the electron pairs are not shared equally. This is because the more electronegative atom pulls the pair of electrons towards itself. Now, why is it characteristic only in heteronuclear atoms? Like, why not in molecules formed by same atoms?
Electron pull is going to be equal there because electronegativity is not going to change. So it doesn't make
Exactly.
sense.
Yes. So electronegativity is the tendency to pull the pair of electrons towards itself by any atom. Now, when you have two atoms that are like of the same element, if you have two same atoms and you have electrons being shared between them, because they are the same element, the electronegativity will be the same. So whatever force this atom is putting on the electrons, same amount of force this one also puts on the electrons, and they both get cancelled. But when you have heteronuclear atoms, so you have a molecule formed with two different atoms, one of them, and then you have the shared pair of electrons. The more electronegative atom pulls the electrons more towards itself, and the less electronegative atom is not able to keep up with that particular force. In that case, now because the force on the electrons is so much more on like from one of the atoms, you see that the electron clouds shifts a little towards the more electronegative atom. So if there is a shift in the electron cloud, there will be more amount of negative charge concentrated on this side. So basically, within the covalent atom itself, you have a partial negative charge on one side, and because electrons are shifting away from the less electronegative atom, you have a partial positive charge on the other side. Okay. So this kind of a bond where the electrons are not shared equally, which is why you have a partial charge separation. Now, this is not complete negative charge. Like the electron is not completely shifted. They're still sharing the electrons, just that one atom has like majority custody of the electrons and the other one has like minority custody. You can think of it that way, right? So you have partial charge only. Like there is more compared to one side of the molecule, there is more positive charge, or like because there is more electrons on the other side that has negative charge, a partial negative charge, and the side lacking in electron has a partial positive charge. So this symbol is called delta. It's a Greek alphabet, and that's used to represent small quantities, tiny quantities. That is why you have partial negative charge is delta negative and partial positive charge is delta positive. Okay. So that kind of a bond is called a polar bond. Now, this does not happen when bond is between two identical atoms because the electron pair is shared equally. So in that case, it's a non-polar bond. So can you give me an example where you would find a non-polar bond?
Chlorine,
Chlorine,
Cl2.
yeah, Cl2.
Cl2, yes.
Nitrogen.
Nitrogen molecule, yes. N triple bond
So
N.
any diatomic molecule will have the same electronegativity, right? So it will be in the middle
Absolutely.
only.
Yes. Pretty easy. So oxygen molecule, hydrogen molecule. So any bond that is between two same atoms is going to be non-polar. Now, what about HCl? Will it have polar bond or non-polar bond?
Polar, because Cl is
Polar
highly
bond.
electronegative, so it will
Very
attract
good. Yes.
electrons.
Very nice. Yes. Water?
Polar.
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 Polar. Yes. What other? What about carbon dioxide?
Non-polar.
But why? Carbon and oxygen have
So
different.
because the if you look at CO2 like you've drawn here,
Mhm.
yeah, we have C, which is less electronegative or very less
Mitali, I've lost your
electrons.
voice.
So if you take like one dipole moment,
Hello?
hello.
Huh. You're back again. Yeah.
Yeah, sorry. So the two dipole, if you look at the dipole moment, it's going to be partial negative on oxygen,
Mhm.
partial positive on CO2, and partial negative again.
Yes.
So if you actually see the partial negatives, they cancel each other out because they're in opposite direction,
Yes. Okay.
and
So
that's why it's not good.
very nice. So that's another important concept when you look at polarity of bonds. Now, because we are talking about charge separation, um, polarity of bonds is quantified, like it's a physical quantity that you can measure, and that particular quantity where how you measure the polarity of bonds is called dipole moment. Dipole moment. So dipole, because there are two poles, a positive side and a negative side, and it is the moment associated with it. Have you guys done rotational motion by any chance? Physics mein?
We're still doing
Yeah.
it. I mean,
You're
my
still
class is still
doing
on.
it. Okay. Have you guys like have you guys heard of something called moment of inertia?
Yes, ma'am.
Mm. So you have an idea what moment is, right? Don't remember it. Okay. So
Yeah.
sort of, yeah. So this particular quantity, um, dipole, like it's the moment. So like related to mass matlab you have moment of inertia. Now because this is related to charge separation, like between two poles, between two oppositely charged ends, you get some this particular quantity is called the dipole moment. I'll just go into what it is. So this is basically like a visual. You can see how the electron cloud is shared between the atoms. All right. So yeah, this gives a better explanation here. So polarity can be thought of the as existence of electric poles. So your north pole, south pole in the magnet are they're magnetic poles. In this case, because you're dealing with charge separation, so you can think of it as electric poles that exist, a positive area and a negative area within the molecule itself. And it is observed for covalent molecules. So this is Dhriti is asking, didn't we do these bonds in state of matter? So we discussed interaction between dipoles, like when you have two different dipoles interacting, like what we discussed in states of matter is basically dipole-dipole interactions. Like if we have two particles in which both of them are dipoles, that's a type of van der Waals forces that we had discussed. Now, yeah, I think we had discussed this back in April when I was teaching you guys dipole interactions, right? Like what dipoles are and all of that. Yeah. And then we discussed dipole induced dipole also, right? So in this case, we'll be looking at where this dipole is actually coming from, right? So within the molecule itself, it is because the electron cloud is being shared unequally between the two participating atoms. So it usually exists when the difference in electronegativities is between 0.15 to 0.16. So if it is less than 0.5, the difference in electronegativities is less than 0.5, it means that, like the electronegativities are very similar to each other. You can think of it as, if they're in the range of um 0 to 4 होता है ना electronegativity का range. So 2.8 and 2.7, it's almost equal to each other. The difference is like 0.1. So it's like both of them, even though it's unequal sharing, it pretty much matches each other out. Even though there will be a little bit of charge separation, it's like practically negligible. You won't even be able to detect it. But as the difference starts to get bigger between this range 0.5 to 0.16, it is much more noticeable. So it's like a clear separation of the charges. You can see here what a polar covalent bond looks like. You have partial positive charge and the partial negative charge, because the electrons are like, they're drifting more towards chlorine because its electronegativity is bigger. And if it is greater than 0.16, like if the electronegativity is like too much, it means that one of the atoms is way more electronegative than the other. So when the difference is too much, like the bond is practically an ionic bond. See, this is
I had a
what is
question.
like observed. Yeah.
Uh,
Yes, sir.
so can we say that if the difference in electronegativities is lesser than 0.5, then the type of bond, like it has London dispersion forces instead of dipole-dipole?
So London dispersion, dipole dipole, all of that is when you have, like, those are interactions between two molecules, two particles that are present in the substance. This we are discussing what type of bond is present within the molecule, between the atoms in the same molecule itself.
Oh, okay, sorry.
Yeah. See? So think of it this way. If the difference in electronegativity is a lot, like, metals are um, metals are basically electropositive. Their electronegativity is going to be like very, very less, like less, almost zero-ish. And non-metals ka electronegativity is going to be pretty high. So the kind of bond you can expect between a metal and a non-metal is going to be ionic because of the high difference in electronegativities. One is way, way, way better at pulling the electrons than the other. So it's going to be ionic. One is just going to pull the electron towards itself. You can see here, the 3s1 electron of sodium is transferred to chlorine. So you basically end up with Na plus and Cl minus.
I have one more question.
Yeah.
I understood that you said that it's between atoms of the same molecule, but let's say for NaCl, if
Hmm.
my one molecule is NaCl and if I had to bond with another molecule of NaCl, would it still be called ionic or will it be called something else?
So then it's not an ionic covalent bond, right? It is interaction between two different molecules. Then you will have one of these van der Waals forces, London dispersion, dipole induced dipole, or dipole dipole, whichever it may be, that way.
So ionic and covalent are only between atoms in the same molecule, but London dispersion and dipole dipole is between molecules of the
Yes.
one.
Yes. I mean, if you consider, London dispersion, van der Waals forces, and noble gases, they are between two separate atoms. But basically, those forces do not end up forming molecules. They're just like, what is the interaction between the particles making up the substance? When you talk about ionic and covalent, it is within the molecule of the substance. Like, if the substance is made up of single atoms like a metal crystal or noble gases, then obviously you're not going to talk about ionic or covalent bonds. So but if the substance is made up of molecules, then you're going to see how are these molecules made, like what is holding these atoms together that they're forming a whole new different substance. Like hydrogen and oxygen make up water. Hydrogen and oxygen can exist independently under certain conditions, and in that case obviously there's going to be some sort of intermolecular forces between hydrogen atoms and oxygen atoms. So there you have to consider, states of matter may whatever forces you have learnt about, van der Waals forces. But water is a whole new substance, also made up of hydrogen and oxygen, but there is something holding together one oxygen and two hydrogens. Now, what is the something that's holding all three atoms together? There you're going to check, okay, what kind of bond is this, ionic or covalent? That way.
But if so, can I say that the forces between I2 or Cl2 or F2? So can
Hmm.
we say that the bond between them is covalent?
It depends on the context you're talking about, Sid. Like if you talk about the force present in I2, are you talking about a single molecule of I2?
Yeah, single
Then that's a
molecule.
covalent bond. But overall, you have a beaker full of I2, and are you talking about the force present between each of the
Yeah.
molecules of I2? Then that'll be LDF.
Okay.
That way.
And but now, if coming to metals, if I have Na, it's
Hmm.
obviously a single atom, so I don't have anything going on over there. Right?
Yeah.
Like I have only that lattice structure that I have to.
Yes. Yeah.
Okay. So in that case, it's just the electrostatic forces between the positive cation of Na and the electron flow, right?
So basically metallic structure that you have, the Na cores and the sea of electrons around the Na cores. That's it. So you don't have any
Oh,
of ionic or covalent bond there. It's just that. Yeah.
okay. Thank you.
Sure. Okay. So okay. Now coming back to polarity of the bonds. Yeah. So this is the range you can predict if the molecule or that particular bond between the atoms is going to be polar or non-polar. So if the difference in electronegativities is large, it's basically, it's like behaving like a metal versus non-metal. You end up with an ionic bond. if the difference between electronegativities is too small, less than 0.5, so like between the same molecules, it'll be exactly equal, difference to zero ho jayega. But if they're between um, two atoms that have very less difference of electronegativity, then it is practically non-polar, because whatever force one atom is pulling it with, the other atom is able to match it. Maybe it's like slightly less, but it's practically matching it. It's not gonna have like a very huge significance. But if it is somewhere between 0.5 to 1.6, if it's like moderate, then the molecule formed is going to be covalent. Like they can only form covalent molecule or covalent compound, and um, that particular kind of covalent compound is going to be polar, like the bond is going to be polar. Okay. So when they are shared equally, charge is equally distributed throughout, there is no polarity, no question of polarity. If they are being shared unequal, you have partial charges on either side. And in the case of ionic bond, there is complete transfer of the electrons. So it's like, you don't talk about polarity of bonds in that case. It's just like positive charge, negative charge. It's not a dipole. You have a single pole of positive charge, a single pole of negative charge. This is the thing. Next. So we discussed dipole moment. So dipole moment is basically the quantified physical quantity uh, by which you can measure the polarity of the bond. Okay, so polar bond gives rise to a dipole moment. It is the measurement of polarity. Measurement, physical measurement, matlab obviously it's got a unit. So the unit of dipole moment is Debye unit. So represented by D. So dipole moment is like the variable used to show dipole moment is mu, is equal to charge into the distance of separation. So 1 debye is basically equal to, now because it's a multiplication of charge and the distance of separation, debye unit is basically coulombs into meter. This is the meaning of the unit, debye unit. And because dipole moment basically depends, it measures in which direction the electrons are being pulled. It's a vector quantity, and if you had to show dipole moment within the molecule, you draw an arrow with a plus sign like this, or a line like this. So yahan pe it's basically the plus shows where the positive side is, and the arrow basically indicates in which direction the electrons are being pulled. The direction of the actual vector is opposite to the direction of electron shift. So this is just the representation, this particular symbol. But when you're, like physical calculations, whenever you're doing it, direction of the actual vector itself is opposite to the direction of the electron shift when you're mathematically representing it. Practically molecule में दिखाने के लिए this basically shows the direction of electron का shift from positive to negative. Okay, so now again, we discussed, Mitali mentioned carbon dioxide में you have the individual bonds are going to be polar bonds, because there is a difference in electronegativity between carbon and oxygen. Oxygen is highly electronegative, carbon not so much. So if I have to represent the dipole moment, how will I represent the arrow over here?
Ma'am, before you
Mhm.
continue, I had one more question.
Yeah.
So if I have a molecule like sulfur, it's monoatomic, right? Like
Uh,
it exists as S, or does it exist as S2 or S8?
so there's S8. Like normally sulfur crystals, you will find them as S8.
Okay, and is there any non-metallic element that's monoatomic?
Noble gases.
Okay, so if I had neon bonded
Hmm.
with another neon, will I say that that's a molecule bonding, or is that, which would I say that that those are atoms bonding to form a molecule?
You tell
But
me.
wouldn't that be like hypothetical?
See, it's simple. If you have a definite bond between the atoms, like it all depends on the force with which they attract each other. So if you have a definite bond where electrons are being shared, like in the case of oxygen, for example, then that's a molecule. It's a clear molecule. You have oxygen molecule, nitrogen molecule, O2, N2. But if it's a very temporary kind of a bond, like that's what van der Waals forces are, right? Like they're one of the weakest forces in the universe. So it exists for a little bit. That's why you have like collision, and then the gas molecules are moving to the other side again. So they exist for a very very short amount of time. They are not like permanently connected to each other that way. So these are like physical forces, and these are like chemical forces. There's not a lot of energy changes that happen in when two particles interact because of van der Waals forces, be it attractive or repulsive, whichever. But
Okay,
whenever there is a formation of bond, be it ionic or covalent, it is always associated with a large amount of energy change. Like depending on the context, either a large amount of energy is released or it is absorbed that way.
and so when I heat something up, when I'm
Hmm.
trying to melt, uh, do I break the bonds between the molecules,
No,
or
again, it depends. When you're doing a chemical reaction, if that's the reason you're heating something, then you're breaking the bond between the molecules. Like, let's say you're producing HCl. So you
no, no?
took.
Let's say that I have iodine,
Mm,
and I want to melt it. Just melt it. I don't want any reaction, nothing, none of that sort. Just
okay.
melting it and
Mm,
breaking the bonds between the atoms or between the molecules.
between the molecules. If you're melting it, it is between the molecules. Whatever
But in
intermolecular forces
a
are there, you're breaking.
reaction is between the atoms.
Yes.
Thanks.
Yeah. Okay. All right. So coming back to representation of dipole moment, we'll start off with like a diatomic molecule only. So we'll go with HCl itself. So HCl may, which is more electronegative?
Chlorine.
Yeah.
Cl. So if I have to represent the dipole moment, which direction should I represent it in? Left to right or right to left?
Left to right.
Left to right, yes. Because Cl is more electronegative, the electrons are shifting towards Cl. तो हमेशा positive side से negative side. This is how you represent it. But if I was representing the mathematical vector, what direction is my vector going to take? Left to right or right to left?
Ma'am, can you
Right
repeat
to left.
your?
Left to right.
It's opposite, right? So it will be right to left.
Mm. So mathematical vector, like when you're trying to represent the vector quantity of dipole moment, like let's say you're plotting it in a graph or whatever, actual vector is opposite to the direction of electron shift. It's like this. So if you want to represent it with something like 3i minus 4j or whatever it may be, so mathematical vector quantity ka direction is going to be opposite to your actual shift of electrons. Yes, no? Guys, still blank or like got it? What?
No, I didn't get the mathematical vector part.
Okay. So dipole moment is a vector quantity, right? So obviously, if you have a vector quantity, you can add it, subtract it, find the dot product, cross product, you can do all of that, right? Now, if it's a dipole, you can think of it as a really tiny nanoscale magnet, basically, polar molecule, because it's got a positive end, it's got a negative end. So obviously, when you're trying to do, let's say, okay, um when you want to figure out the magnetic properties of a particular compound like HCl, this is a polar molecule, it's got a specific positive end, it's got a specific negative end, which means that it needs to behave in a particular way when you put it in a magnetic field. So whenever you want to do the physical calculations representative of that, you will need to take numerical value of the vector, right? So this is what I meant by the mathematical vector quantity. So when you're doing actual mathematical calculations of it, the direction of the vector that you take is opposite of the actual direction of the electron shift. It's like, for example, you guys have studied about electricity, right? What do you mean by a current and electric current?
A flow of
Flow of
electrons.
electrons.
For a flow of electrons, right? Now, whenever you're talking about direction of flow of electrons versus direction of current,
It's opposite.
it's the opposite, right? So like similar logic. So direction
Okay.
of the vector that you'll consider in your actual calculations when you're doing, when you're using this in your research or whichever it is, the direction of the vector of this
It's
dipole
opposite to the
moment,
dipole moment.
yeah, it's opposite to the direction in which the electrons are shifting.
Okay.
That's what. Okay. And because it is a vector quantity, that's why carbon dioxide, even though individual bonds are polar, in this case electrons are shifting towards oxygen, electrons are shifting towards oxygen, because both the forces are going to be equal, क्योंकि दोनों तरफ oxygen है, overall net dipole moment, both of these forces get cancelled with each other, and carbon dioxide is a non-polar molecule. Okay, we'll do some more examples on polarity. Polarity is very, very important because you will come across these concepts again when you're talking about organic compounds. So organic compounds may figuring out, knowing where the positive centers are, like electron rich centers are, electron deficient centers are important, because that's how you'll be able to predict your reaction mechanisms. कि अच्छा मेरे पास एक OH minus ion है and it's acting on so and so particular organic compound, तो किधर जाके it's going to attack. So like figuring out all that reaction mechanisms and all, these are the basics that you're going to use again and again in all of that. Okay. All right. So in polyatomic molecules, the dipole moment depends on one, bond dipoles, which is basically the individual um, uh, dipole, or the polarity of the bond itself, like each individual bond. And second, it also depends on the spatial arrangement, because the spatial arrangement will decide the total dipole moment in a molecule, because all of them are vectors, so the total dipole moment is going to be the vector sum of individual moments. You
I had a
guys have
question.
you guys have practiced vector sums, right? How to add vectors, subtract vectors, all of that.
Yeah.
Yeah.
Cool. Sid? Yeah.
So I wanted to ask about organic compounds. So will they be non-polar or polar?
So it depends. Like you can't just give a generalization. So we'll come across this, like all these examples, we're going to work with this. So you'll observe that one, two, three of them, नहीं PF5 नहीं होगा. हाँ, these three are organic compounds itself, but polarities is going to differ between all of them. So it depends on the molecule, and that's what I'm going to practice now. Identify whether it a thing is polar or non-polar. Okay. I'm
So
going to
can
move.
you generalize it for each group? Like, can you say that alkanes as a whole are non-polar or polar?
Alkanes. You tell me. Do you think alkanes are polar or non-polar?
Uh, I have no clue,
We're
to
gonna
be
figure
honest.
that out. You'll be able to figure it out in the after like 10 minutes after some practice.
Okay.
Okay. So dipole moment, like the net polarity, you can decide after figuring out what the total dipole moment is. So total dipole moment figure out करने के लिए you need to know what is the vector sum of all the individual dipole moments. Okay. So the first is when you have HCl. Is this polar or non-polar?
Polar.
Polar.
Because एक ही bond है और उसका specific direction भी है. Cool. Let's look at BCl3. So boron trichloride. This is the shape of the molecule. Okay. So this is like all of them are, this whole shape is pretty symmetrical. Like if you join the three chlorine atoms, you'll get an equilateral triangle. Now boron and chlorine, there is a difference in electronegativity. Electrons are going to be shifting towards chlorine. What will be the net dipole moment in this case?
0.
0.
Okay, Mitali and Mayas have said 0. What about the rest of you?
Even I think 0.
Ishita also says 0. Dhriti, Sid, Tarannum,
Upward.
what do you think is the net dipole moment in this? Okay,
I
Dhriti
think it's
and Tarannum. Yeah, Sid, you think it's
upward.
upward? Okay. So total dipole moment is the vector sum of the individual dipole moments. So you have one vector which is over here and the other two which are over here as a angle between all of them are equal. If
Oh
you
yeah, got it.
add all these three, what will the net vector sum look like?
It is 0.
0. So
0.
in दोनों का sum will be magnitude same होगा and it's going to add up to directly opposite of this and ये दोनों cancel हो जाएंगे. It's going to be 0. ठीक है? All right, another one. Do you guys know what a tetrahedron is?
Yeah. So like
Something like yeah.
tetrahedron is no, go ahead. It's okay.
Okay, so tetrahedron is like a kind of a, it's sort of like a pyramid, but it has 4 sides.
4 faces. Like yeah, it's basically a
Yeah.
pyramid with a triangular base. Yeah.
Yeah.
ठीक है. But do you know what it means when a molecule has a tetrahedral shape?
So can I take an example?
Yeah, sure.
CCl4 or
CCl4. Okay,
CH4,
that
they're
works.
tetrahedron because one bond is upwards and three other bonds are in the form of a pyramid. So like a carbon being the top, and one is like, so like in this example, one Cl is like inside the plane, one Cl is outside, like that.
Kind of. So it basically is like when you join all the 4 chlorine atoms, you're going to get a tetrahedron. You're going to get a pyramid with this thing, and carbon is at the dead center of the tetrahedron. Okay, so it's basically a 3D symmetrical shape. Um, yeah, like where all the angles are equal to each other. Whichever angle you measure in whichever direction, it's equal to each other. I'm just gonna switch on my video so that I can give a demonstration of what it looks like. I'll just stop the share so that screen is bigger. Okay. So I've got like 4 pens over here. So tetrahedron basically looks like this. So you have one at the top and the remaining 3 are placed symmetrical this way. And this whole shape is so symmetrical that it looks something like this, right? If I rotate, if I get this one on top, you'll like essentially end up with the same shape. So it's like it it's symmetrical in a 3D sense this way. And if I get this one on top, so if I join the tips of all these 4 sides, I'll end up with a pyramid with a triangular base. So that's what a tetrahedron is. Now these 2 should be like this. This should be exactly on top. Okay, it looks something like this basically. Anyway, so we'll come across this even when we're doing VSCPR. तो और अच्छे से idea आ जाएगा उससे. Okay.
Ma'am,
Yeah.
ma'am, I understand like how the vector, how do we use vector in these types of questions, but like I don't know how to draw these things. Like,
Oh,
is that fine
that,
or?
that's fine. Like you'll eventually end up learning it when we do VSCPR, right? So you'll end up learning it, no problem.
Because if somebody gives me a drawn figure and asks me where the what do we call dipole moment will be, I would be able to guess, but without the structure, I don't know.
So you will need to draw the structure. So if I give you a molecule like CCl4, so do you इसके लिए you would need to know what is the shape of CCl4 and then you'll be able to figure out कि अच्छा dipole moment कैसा है. And the shape of CCl4, that उसके लिए once we do VSCPR, that gets more easy. Okay, so don't worry about it like right at this moment. Abhi ke liye we'll just learn, given the structure, can you figure out what the dipole moment is going to be? Okay.
Okay.
All right. So we've been discussing tetrahedron. It is symmetrical from all sides. So what do you think would be the dipole moment in CCl4? It has to
Zero
be
Zero
or
only.
J.
Zero
yeah.
only, yeah.
0. Everyone agrees or anyone disagrees?
0 only.
0 only. Correct. Because it's perfectly symmetrical, right? So all the 3 downwards, if you do the vector addition, the dipole moment will end up exactly opposite side to the top part का dipole moment. So magnitude same है, direction ये हो जाएगा. These 2 get cancelled. Do you guys know what chloroform is? What is the formula for
I don't
chloroform?
know the formula.
Oh,
Yeah.
but you guys are aware of chloroform now. It's a very simple compound. Yeah. So it is CHCl3. So basically CCl4 mein instead of chlorine you have 1 hydrogen. This is chloroform. Okay.
This is a substitution reaction, right? It's
Yeah.
formed from the substitution reaction.
Yes. Correct. Okay. So But again, carbon is bonded to 4 atoms, so structure is still going to be tetrahedral only. But one of them, there is hydrogen. Now, net dipole moment क्या होगा इस molecule का?
Upward.
Downward.
Downward.
Yeah, downward. Sorry.
Okay, everybody agrees that there is going to be a dipole moment, or is there, or do you think it's going to be 0?
I think it's 0.
Okay.
I
Why?
don't think it. Sorry.
Both of you say what is your reason.
Because it is symmetrical.
Okay.
My reason is that because we don't have like a Cl upwards anymore, the dipole moment between carbon and hydrogen will be downward because carbon is
Yes.
more electrovalent than hydrogen.
Correct. So electron shift in all these 3 cases is going to be downward. Net downward है. If you consider carbon and hydrogen इन दोनों के बीच में dipole moment, carbon is more electronegative, so ये भी downward होगा. So you have 2 vectors in the same direction. Okay, electron shift will be downward, matlab vector is going to be upward and upward. तो total net dipole moment क्या होगा?
Downward.
Upward and upward, so electron shift net is going to be downward, or like the net vector is going to be in the upward direction. Okay.
Ma'am, I have a question. Here says that the dipole moment is opposite to that of electron flow, right?
Huh.
So, could you say that if carbon's more electronegative than hydrogen,
Mm.
electrons move from hydrogen to carbon,
Yeah.
so shouldn't that movement be upward?
So electron shift is going to be towards carbon, so that's why downward. The dipole moment is going to be upward, or the vector of the dipole moment is going to be upward. Yeah, that's what I'm saying. So electron shift, this thing is going to be downward. Like if you're representing with this part, it'll be downward. The dipole moment ka vector is going to be upward.
So net dipole moment should be upward.
Yeah. So the net dipole moment is upward. The net electron shift, the net polarity is going to be downward. Okay. Right. So yeah, you guys are getting the hang of it. That's good. So you know that, okay, so it basically depends on both the spatial arrangement, तो क्योंकि vector addition कर रहे हैं, and also the individual like the individual polarities. So जहाँ पे भी individual polarities are all same, but the molecule is like symmetrical, तो पूरा cancel हो रहा है. That is why the net dipole moment is 0. But in the cases where it is not symmetrical, you're ending up with a net dipole moment. So you can see here, HCl में है net dipole moment is in blue. BCl3 में the net dipole moment is 0 because it's perfectly symmetrical. In CH2O, this is basically formaldehyde. It's an aldehyde compound, organic compound. There is a net dipole moment because you can see how the vectors are adding up here. So CH के बीच में in like electrons are shifting in a particular direction, and carbon oxygen ke beech mein the electrons are shifting upwards, so all of them add up and the overall net electron shift, it is in the upward direction. This is going to have a net dipole moment. Ammonia again, so this has a pyramidal shape, so the net is going to be roughly in the upward direction. CHCl3 also we just discussed. CCl4 again, because the individual values are all equal, to cancel hoke the net is 0. TF5, this is also a symmetrical compound. Niche 3 add up to 0 and ऊपर और नीचे भी they add up to 0. Okay. So this is how you figure out the polarity of any molecule. And polarity is important because, in short, if we didn't have polarity of water, life would not exist. Like, because water is a polar molecule, other polar substances can dissolve in water even though water is covalent. uh, and like, you have the dipole-dipole interactions which help in the solubility of a substance. um, Polarity is also, like, apart from being able to check whether, okay, something's gonna dissolve or not dissolve, depending on the quantity of polarity, it gives rise to a lot of other properties also. um, Electrical properties, magnetic properties, and all of that. Okay, so it's quite important knowing the polarity of any particular molecule. All right. Oh, this is another interesting case. So we are comparing ammonia, which is NH3, and NF3, like nitrogen trifluoride. Two molecules, their structure is the same, but even though the structure is the same, the net dipole moment is very different from each other. Like, the direction itself is
The
different.
opposite, right?
Yeah,
Yeah.
the direction is opposite, plus the magnitude also is like so different from each other. And the reason is that you can see one is the direction of the individual, what do you say, the individual bonds.
Dipole of
Yeah, the individual bonds between nitrogen hydrogen versus nitrogen fluorine, the direction is going to be different because difference in electronegativity is different. Like, hydrogen is less than nitrogen, but fluorine is greater than nitrogen. And secondly, nitrogen has one lone pair of electrons, right? So nitrogen has 5 electrons outer shell may, 3 of them are used in bonding, leaves it with one lone pair. So the lone pair of electrons also contributes to figuring out what the net dipole is going to be. So you have lone pair of electrons ka negative charge plus the electron shift ka partial negative charges, adding to a greater dipole moment. But in this case, you have a negative charge here, and partial negative charge is going in the other direction. So which is why NF3 has a lower net dipole moment. So in this case, the lone pair of electrons ka negative charge is differing from the partial positive charge that is there on nitrogen, which is why it is reduced. But in this case, it is reinforced. Nitrogen pay negative charge due to the electrons as there, plus it is pulling the electron clouds towards itself. So, the overall charge is reinforced, which is why you have a higher net dipole moment. So yeah, so the lone pair of electrons that is present on nitrogen is another thing that you have to consider. Okay. All right. So clear about polarity of covalent bonds?
Yes, ma'am.
Okay, cool. And just like how we have polarity in the case of covalent bonds, um, we also have, like, ionic compounds also take a partial covalent nature. So yeah, ionic compounds are formed because of the attraction of cations and anions. But these individual anions also have like electron cloud around them, right? And when you place both of them beside each other, there are chances that the electron cloud shifting a little bit, and it takes on a bit of the covalent nature where the electron clouds are surrounding the cation also. This is not very high, like the bond does not get converted to covalent, but there's a bit of covalent nature of the compound. Okay, so this scientist Fahans, he postulated some rules that predict the covalent nature of the ionic bond. So one is smaller cation or a larger anion Like if the cation is smaller or if the anion is larger, that results in greater covalent nature. Okay. So when you're comparing LiCl and KCl, lithium smaller cation would have more covalent nature than potassium chloride. Now, why is this important? Like, why are we talking about covalent nature is, um, you know, the properties of ionic compounds, that ionic compounds are soluble in water, and when they dissolve in water, they dissociate into ions, they conduct electricity and all of that, right? Now, greater the ionic nature, the better these properties will be. So when you're comparing LiCl and KCl, maybe KCl being more ionic will be more soluble compared to LiCl. Like solubility of KCl would be more compared to the solubility of LiCl that way. So knowing which has greater or lesser covalent nature will help you in predicting these kinds of properties. Similarly, larger anion results in greater covalent nature. So if you're considering only anion, iodide is larger than fluoride. So NaI has more of a covalent nature compared to NaF that way.
Why is that the case?
Hmm?
Why is that the case?
Why is this the case? Think of it this way. When it comes to smaller cation, cation is smaller. So when you put a positive charge, like a positive cation has, like you have a positively charged kernel, lattice may, this will be placed to a negatively charged ion. A smaller cation, so the positive charge of the cation is because of greater number of protons in the nucleus, right? So this will have more of a tendency to attract the electron cloud from the anion, giving it a slight covalent nature. And that is why the reverse is case with the anions. So if you have a smaller anion and a larger cation, okay, so larger cation will not have like enough force to attract the electron cloud towards itself. Smaller anion matlab it is going to hold on to its electron cloud tightly, like it won't be able to let go of it easily, which is why a larger anion results in a greater covalent nature. Like think of, you have a cation, you have an anion with an electron cloud. Of course, you know, yeah, there are electrostatic forces of attraction, but again, when you think of electron as, you know, a cloud, not as a particular particle, it's not going to attract the whole electron towards itself, because obviously that's not the case. Like it defeats the purpose of forming a cation, but it might attract part of the electron clouds towards itself, giving rise to a slight covalent nature to the bond. Does it make sense? Clear?
Not entirely.
Mm-hmm. Uh, can you tell me where you're stuck? Like what part?
I mean, um, I don't understand why the size of a molecule even has any place. Like, I would say that I would argue that NaF should be more soluble because I would say that fluorine is more electronegative, right? And Na is less electronegative, which means that shouldn't the dipole difference shouldn't the dipole difference be more in that case?
Yeah, NAF will be more soluble, like because this will have more ionic nature. You're right.
Oh, sorry, I read it wrong. My bad. I read that. Yeah,
Ah,
yeah.
yeah,
Okay, yeah.
yeah,
Then I get it.
cool. So smaller cation, more covalent nature, larger anion, more covalent nature. So opposite charge, opposite effects. Okay. Similarly, a greater charge on the cation results in a greater covalent nature. So within a cation or an anion, like if you have aluminium 3 plus compounds, you can expect more of a covalent nature of these compounds as compared to Na plus compounds. Okay. And cations with pseudo noble gas configuration, like for example D block elements, where their third shell is complete, they don't have a noble gas configuration, like they don't end with ns2 np6, but like their D shell, like 3s2 3p6 3d10 or 3d whichever, like cations with a pseudo noble gas configuration where it's n-1 dn and ns0 will have greater polarizing power. So like that's what it's doing to the ionic bond, right? Like it's polarizing the ionic bond, so it's not maintaining that clean separation of charge. So basically it gets more covalent nature as compared to cations with a pure proper noble gas configuration. So basically D block elements will have more of a covalent nature as compared to your S block elements. So these are the three of Fahan's rules, who basically gave the flip side to the polarity of a bond. Like what if you have an ionic compound, then there are ionic compounds, like depending on the participating elements, like they do have the power to polarize the bond between them. It's not a complete separation of charges. That's important because that basically affects, like you'll be able to predict um, the solubility or the conducting properties. Like some of them are strong bases, some of them form weak bases, some of them are more soluble, some of them are less soluble. Like where is this difference in properties within ionic compounds coming from? So that's because of the polarity of the bond. So smaller cation or a larger anion results in a greater covalent nature, or the greater polarizing property of the bond. A greater charge on the cation means more polarizing, greater covalent nature. And again, D block elements in general, like if that particular compound has a pseudo noble gas configuration, like Fe2 plus, right? If you consider Fe2 plus, it has only lost the 4s2 electrons. It still got the 3d electrons. So those kinds of ions will have greater polarizing powers as compared to your S block, like cations with proper ns2 np6 configuration. Okay. And then we come to VSEPR theory. Do you guys want to take like a 2-minute break? Do you want to see, like, do you want to like solve some questions before taking on VSEPR theory?
Yes, ma'am.
Okay. Take like a 2-3, like it's 4-7 right now. We'll resume at 4-10, and we'll do a bunch of questions before starting with VSEPR, because I feel like this has been a lot of information. We haven't done any questions yet. Okay.
I had a question.
Yeah, Sid.
So, if we go across a period, and
Mm-hmm.
if I have, let's say, if I have, just a second, um, if I had a ionic compound of lithium, and then I had an ionic compound of beryllium,
Uh-huh.
which one would be more soluble? Will there be a difference?
Yeah. So based on, like, if you compare lithium and beryllium, which one is going to have more charge?
See that's where I'm confused. So, is it that if I have more electrons, then will the net dipole moment increase, or will it
So in this
decrease?
case, you're not like it's not a dipole that is being produced, right? Yeah, there's just a little bit of polarizing power that the ions have.
No, no. So
So
if I have more electrons, will the influence of the nucleus decrease, or will it be unchanged, or increase? Or I know that the number of protons is also increasing. So in
mm,
that case, would it have a higher strength?
higher, so greater charge on cation means greater covalent nature. So
Okay.
beryllium is going to have more of a covalent nature as compared to lithium, which kind of stands, right? Like when you go from left to right, if you want to compare what kind of bond, let's say, an element in that period forms with something like chlorine. So lithium is going to form purely ionic bond with chlorine. And if you go all the way on the right side of the periodic table, like nitrogen, oxygen, fluorine are going to form purely covalent bond with chlorine because they're non-metals. So basically, when you go from left to right, the polarizing power or the covalent nature of the bond increases. So
Okay.
even though beryllium forms, say, ionic compound, um, it will have more covalent nature as compared to lithium that way. All right, so let's resume. I'll just put a message here. Okay, you guys ready? Questions के लिए?
Yes, ma'am.
Cool. Can you guys message Tarannu? She was here. I think she got disconnected a bit. Just check on her. All right. Lewis approach, Lewis dot symbols, Lewis structure for ions, ये सब तो easy है. Define octet rule, ये सब theoretical है. So this we don't need to. Explain the formation of a chemical bond. Explanation. Alright, 4TB6. Choose the compounds containing ionic, covalent, and coordinate bonds out of the following. We haven't discussed coordinate bonds yet, have we?
No.
Okay.
Ma'am, I have one more. Uh, so, would this same theory stand for hydroxides, the solubility theory? So if
Yeah,
I have
any
KOF,
yeah,
any
any yeah,
ion.
any ionic compound, yes. So solubility के case में it doesn't purely depend on the ionic covalent nature. Like obviously this is definitely a factor. Apart from that, you have something called solvation enthalpy, enthalpy of hydration, and all of that, which we'll look at when we do thermodynamics. But yeah, this is one of the cases that affects solubility.
Okay, thank you.
Yeah. All right. So ionic compound you're aware of, covalent compound you're aware of, coordinate compound. So coordinate compounds are basically the kind of bonds in which the pair of electrons being shared between two atoms come from the same atom. Like for example, we had seen ozone का ozone तो इधर ही है, और कौन सा example, we'll go with ozone only. Okay, so we've seen ozone का structure where you have O double bond O and single bond O, right? Basically what is happening is one lone pair on this oxygen is being shared by both of these oxygen molecules. So it's not a regular single bond in which only both of them are putting in one electron each. That's not what's happening. Both the electrons, the pair of electrons is going from oxygen to this other oxygen atom. Another example is carbon monoxide का structure जब किया था हमने. So you had C, one lone pair, double bond O, and you had a triple bond here, right? So the third bond is basically one of the lone pairs on oxygen being given from oxygen to carbon. So both the electrons, like both the electrons in this particular pair is being donated by the same atom itself. So that kind of a bond is called a coordinate covalent bond. Okay.
How do you represent a coordinate bond?
So sometimes they're represented like normally itself. Sometimes you represent them with an arrow like this. Like nitrate में भी you have a double bond and एक ऐसे जाएगा ऐसे, that kind of a thing. So sometimes it's represented by a arrow and sometimes it's represented by a dotted arrow. So usually you have something called coordinate compounds which D block compounds exclusively form. वो तो बाद में 12th में you're going to we're going to go in depth about it. Complex coordinate complexes you call them. So in those cases I've seen it represented by a dotted line, but otherwise you just represent it with an arrow showing that acha, the same atom is contributing, like यहाँ से यहाँ जा रहा है वो pair of electrons. All right. So MgCl2 में what kind of bond is it? Ionic, covalent or coordinate?
Ionic.
Ionic.
Ionic, sure.
Yes.
Yeah. CH4?
Covalent.
Yes, covalent.
Riti, Ishita, Sid, Tarunum?
CH4 is covalent.
Covalent, Shah? Okay. CV. CaO, calcium oxide?
Not sure, but ionic.
Ionic
Yeah, ionic.
is a metal, so yeah.
Yes. Calcium is a metal +2, oxygen is a non-metal -2. So this is ionic. HCl?
Covalent.
Mm-hmm. HCl?
Ionic.
Oh, no. Wait, what? Sorry.
No, HCl is covalent, right?
Yeah, it's covalent.
It's covalent.
Yeah.
It's polar, but HCl is covalent.
Ma'am, why is it not ionic?
Because they're like you don't have H plus and Cl minus happening separately. There is a bond between H and Cl.
Okay.
Okay. Yeah. What about ammonium ion? NH4 plus.
That should technically also be covalent only, right?
It's
but I'm not sure. Mainly covalent.
Coordinate.
It should be coordinate.
How?
4 plus.
Yeah, it's like a iron.
Are you can be a little descriptive also. Like you can say, acha, do ionic, do like, or
Actually,
two of them are coordinate, two of them are covalent. Yeah, one is ionic. Like you can be a little descriptive also if you don't think it fits in one.
nitrogen. I mean, not nitrogen. Sorry.
It should have three covalent
Ammonia.
and one coordinate. Yeah,
Yeah,
sorry.
it's ammonia is practically covalent, and this is coordinate.
Exactly.
Yes, absolutely. So that's exactly how ammonium is being, ammonium forms also. So ammonia may the three hydrogens you have three covalent bonds. Nitrogen has a lone pair of electrons, and usually acidic media, or when it is dropped in water, uh, it attracts an H plus. So this lone pair of electrons is donated to H plus ion, and that's how your ammonium ion is formed. Okay. So that is the reason why ammonia has basic properties. So it's called a proton acceptor. Anyway, we'll discuss all of that in length later. Okay, so yeah, three covalent bonds between nitrogen and three of the hydrogens, and one of them is a coordinate covalent bond. Very nice, good, good. ओजोन, ओजोन तो अभी डिस्कस किया, क्या होगा?
Two covalent and one coordinate.
Yes. So you have a covalent double bond or a double covalent bond and one coordinate bond. Yes. Cool. What are the favorable factors for the formation of ionic bond? ये कल ने परसों डिस्कस किया था. So you'll have to answer in terms of energy values, the relevant energy values.
Oh, low ionization enthalpy and
Yeah.
high energy.
High what energy?
Electron
High,
gain enthalpy.
Huh.
exactly. Sorry.
That's it, or are you missing something?
And high lattice enthalpy.
Yes. Yeah, don't forget about lattice enthalpy, because if that is high enough to compensate the other two, the ionic bond will still be formed. Okay, so low ionization enthalpy ताकि cation easily बने, high electron gain enthalpy ताकि anion easily बने, and high lattice enthalpy so that the compound itself can form easily.
Ma'am, we only talk about lattice enthalpy when we're talking about ionic compounds, right?
Yeah, lattice
Okay,
enthalpy applies to ionic compounds. Yeah,
okay, ma'am.
wherever a lattice structure is basically formed. What is ionic bond? Right, two suitable examples uh, to show the difference between ionic and covalent bond. ये तो you guys can do it. अच्छा, if anyone wants to discuss this, let me know, huh? I think it's a simple question, so I'm skipping it. Bond parameters, define, definition तो लिख सकते हो. Indicate whether following statement is true or false. Justify your answer in not more than 3 lines. Dipole moment of CH3F is greater than that of CH3Cl.
It's true.
And justify.
F is more electronegative than Cl.
So,
So like CS3 is gonna have it's common between the two. So and as F is more, the dipole difference is gonna be higher, and therefore.
yeah. So you don't say dipole difference. You say the polarity is going to be higher. You can say that.
Okay, my bad.
And hence the dipole moment is greater.
Yeah.
How do you express bond strength in terms of bond order? So basically, uh, like bond strength
And more
highest.
bond order means more bond order. Directly proportional.
Huh. You said more bond order means more bond order, Mayas.
Okay.
So more bond order means more bond strength. Yeah. Explain the terms. Well, meaning of the terms तो देख के कर सकते हो. What is meant by the term average bond enthalpy? Is there a difference in bond enthalpy of OH bond in ethanol and water? Is there?
No? I mean, I'm not talking in terms of the molecule. I mean, I'm assuming they're not talking in terms of the molecule.
Why
think
would
ONH or OH as a whole with the other.
Yeah.
bond enthalpy of OH, whenever it's written like that, it's basically OH O और H के बीच में वाला bond.
Huh. So,
Yes.
ma'am, then I don't think there will be any difference.
Why?
Because you said you're talking only about the O bond H thing, not O bond H in terms of the molecules.
There is difference, I think.
There would be difference, no? Like, yes, the participating molecules are the same, but you also need to see water में this is connected to
There
H.
is one H.
And ethanol में this is connected to carbon, which is in turn connected to whole other different things.
So the bond enthalpy in ethanol will be more than water, right? It's like huge compound. I don't know.
No,
That
there,
thing we
yeah,
cannot guess now, right now.
more or less,
But
like you won't be
you,
able to say. So here they're
okay.
just asking, will there be a difference? And why is there a difference?
Why, ma'am, is there a difference?
Because the context, like um, what they are attached to is different. Like this
Okay,
oxygen is only attached to hydrogen. So,
correct.
and we've also seen how polarization, like, the polarity of bond also is affected depending on what it is connected to. So all these
We can
factors
explain
play a
this
role.
with an example also.
Like you don't need to. They've given the example directly here. You just have to write it in one statement that both the bonds are not equivalent because they are present in two different compounds. Like in one case, oxygen is connected to another hydrogen. And secondly, when you're talking about bond enthalpy of OH, you're going to consider the average bond enthalpy. But in this case, there's only one OH bond, so you're just going to consider whatever energy is required to break this. So that's why it's not going to be the same. Okay. Define electronegativity. How does it differ? Okay, this we've already discussed. Pehle. Do you guys remember the difference between electronegativity and electron gain enthalpy?
Yes, ma'am.
Arrange the bonds in order of increasing ionic character in the molecules. So you've got LIF, you've got K2O, you've got N2, you've got CO2, you've got SO2 and ClF3. So increasing ionic character matlab most covalent to least covalent. Or like most covalent to most ionic. This is a very good question. Think about this.
Would N2 be the first one?
N2, yes, because it is equally shared. Then
I would say ClF3 after that.
Okay,
CO2. Sorry. I'll write my thing and put it in the chat box.
ठीक है. Sid, you said ClF3. What's the logic behind that?
Their electronegativities are very close together, so I would say that
Very good.
polarity.
Yes, absolutely right. Then
Now I'm
N2O
contemplating
gas
between
helps.
CO2 and SO2. I
Hmm.
I think SO2.
SO2 more covalent than CO2. Why?
They're part of the same group, so I believe that the
Wait,
electron movements
she's saying,
S
acha, S and O belong to the same group. Acha, वैसे. Very good. Yes.
and CO2.
Okay. Then
Um, K2O.
K2O. K2O or LIF.
Fluorine is really electronegative. I know that much.
Mm. Now both of these are
But similar,
ionic
I would.
because they both are metals. So now look at charge, like a combination of charge and size of the ions.
Look, K and I is gonna Li is gonna have the same charge. Yeah, same charge
Charge
because
same hai. Yes.
uh, no, O has the two minus charge, but F has one minus charge. But would
Hmm.
that play a role over here? Because I know for sure that F is more electronegative than O.
Yeah. So recall
But if
Farn's
you look
rules.
at if you talk about Fahn's rules,
Mm.
it says the greater charge on the cation results in the greater covalent nature.
Yes.
So if you take LIF and K2O,
Hmm.
if you look at the charges, both of them have 1 plus, so that I'm not considering. But F has -1 and O has -2.
Hmm.
So technically, it should be K2O and then LIF.
Okay. What about size of the ions?
O is greater than F, so larger anion will
Yes.
have more ionic nature.
But it's also a larger cation.
So larger
No,
anion has more ionic nature.
but
Uh,
if you, sorry,
No, no, larger
no,
anion has
wait,
less.
huh? Larger anion
Uh,
has less ionic nature. And if you compare between cations,
but you can eliminate that because F is lower and so is Li. So it and K2 is greater and O is also greater. So you can I think you can eliminate that out. You
but
can't
if
you
you see, because Li and F are like small atoms compared to K2O, the covalent character, because they're like first elements as well, the covalent character is mainly higher than K2O,
hmm,
right, ma'am? Because it's small in size, like that's the entire the first elements of the group anomaly thing.
but oxygen is also the first element.
oxygen is first, but
God.
potassium is not, no?
Yeah,
Yeah,
but
see,
larger than F and K2 is it's larger than Li. So they both like you need
In
a
which,
you,
okay, think about it in this way. In which case do you think the difference in electronegativities will be larger?
I think LIF.
LIF
LIF or K2O?
difference.
Difference in
Ma'am,
electron.
because F is the most electronegative compound there is. Array,
Yes.
element there is.
Hmm.
I would say
And
LI.
yeah, even I would say LIF.
So you're saying alive. See, F oxygen closely follows fluorine. Like fluorine is the highest electronegative compound there is. Oxygen is second in the periodic table.
Okay, then LIF will be the LIF would be more covalent than K2O.
Hmm.
I wasn't aware of the I can't
Yeah.
really make a decision about them.
I forgot
So
what my initial answer was. Sorry.
this is how you like reason it out. This is how you figure it out. So difference, if you consider the difference in electronegativities, oxygen, so fluorine is most electronegativity negative compound followed by oxygen, which is why even like we've seen some cases where noble gases are forming compounds, right? So no, like noble gases, especially only the higher ones, you see only xenon forms largely and krypton to some extent. Krypton forms only with F, but xenon forms only with fluorine and oxygen, not with chlorine, not with any other element at all. So F ke baad सीधा second place in electronegativity is oxygen only. This is like one thing you can take for sure. But difference in electronegativity, if you compare lithium and potassium, potassium would be way less on electronegativity compared to lithium, and its size also like basically doesn't help. Like I would say K2O tends more towards ionic side as compared to LIF. Okay, so CO2 के बाद LIF आएगा and then K2O will be the most ionic. Yeah, cool. Got it?
Yeah.
Yes, ma'am.
Yeah. Next, why are some covalent bonds polar? What is a dipole? Okay, ये सब तो theoretical है. Arrange the following sets of molecules in decreasing order of bond angle. This will get easier once we do VSEPR. So I'll not do this abhi. Okay. उसके बाद VSEPR hybridization, hydrogen bonding, give reasons. Okay, you guys want to do more questions or are you guys ready to do VSEPR now?
Yes, EPR.
Yeah, ma'am. I mean, PSCPR.
Okay, cool. All right. VSEPR, how many of you think it's difficult or, it's like, how many of you would rate your concept less than 6 when it comes to VSEPR?
I've never really done it, so
Okay.
I can't say.
So VSEPR is very, very easy. There is nothing to this. There's only one plain simple logic that we are going to, apply to figure out what is the shape, what is the geometry of a molecule. Isme all you have to know is how many bond pairs are there and how many lone pairs are there. So once you know how many bond pairs, how many lone pairs, you'll easily be able to figure out what is the shape of the molecule. Okay. So VSEPR is full form is valence shell electron pair repulsion theory. It seems like some random words just put in together, but there is a logic to it. So this whole theory is basically designed to give you to predict the shape of covalent molecules. And how do you predict? You check valence shell में what all electron pairs are there. So based on this, it will give you an idea of what sort of repulsions you will find. So this is going to help you figure out the best possible positions of where the bonds will be aligned towards. This is what this whole theory is about. So इसलिए whenever you want to predict की geometry क्या होगा, geometry मतलब what is the shape of any covalent molecule, you check valence shell में कितने सारे electron pairs है. How many bonding pairs, how many lone pairs. तो उसके basis पे you'll be able to figure out the shape. So it was based on the repulsion between electron pairs in the valence shell of atoms, developed by so and so people, and it's refined by so and so people. Fun facts. So these are the postulates. I don't think you'll have to learn these postulates. The main kind of questions you'll be asked is what is the shape of the molecule, and maybe to draw. Like, that's all. So anyway, so postulates first, the shape of the molecule depends on the number of valence shell electron pairs. Now this I just said based on the name only. So you have to check how many bonded and non-bonded pairs are there, and that will decide the shape of the molecule. Now, how do we know what shape they're going to take? That is because electron pairs repel one another because they're all negatively charged. And because they repel each other, they tend to occupy positions that minimize the repulsion. So repulsion minimize करने के लिए you need to maximize the distance between each of these electron pairs. So a simple hypothetical example, if I take एक atom है, it has two bond pairs. Excuse me. Sorry. Sorry about that. Okay. So there is an atom. It has two bond pairs. Now the two bond pairs can be aligned in any way. Like you can have one bond pair ऐसे and the second one ऐसे. Another way you can have one bond pair ऐसे, one bond pair ऐसे. Another one you can have one bond pair यहाँ पे, one bond pair यहाँ पे. Or you can have central atom and one over here, one over here. Like it can be oriented in any way, in any direction, right? Amongst these four cases, A, B, C, and D, which case do you think will be most comfortable for the atom? So considering that the electrons that are there in the bonds are repelling each other, which case will be most comfortable for the atom, the molecule to have?
B.
B. A तो obviously इतनी close पे तो they'll repel each other, exist ही नहीं कर सकता है. C and D ठीक है, distance ज़्यादा है, but this will be the best case scenario because distance is maximum. They're on opposite sides of the central atom. Okay, that's what it's saying. So electrons repel one another, so they tend to occupy positions that minimize the repulsion. That is, maximize the distance between each other. The valence shell is taken as a sphere and the electron pairs are localized at maximum distance between them. Okay, so the way I have drawn it here. So Lewis Coastal structure mein Lewis said valence shell is a cube because octet complete hona chahiye. VSEPR cube ko basically sphere bana diya. Matlab it, like, imagine a ball and you have to stick, say, chopsticks on the ball. So you stick these chopsticks such that there is maximum distance between these chopsticks. That's basically the visualization that you can have. So even though there's multiple bonds, double or triple bonds, they're treated as a super single bond. So let's say you have carbon dioxide, you have double bonds. Even though there is double bond here, for the sake of knowing geometry, VSEPR treats it as a super single bond. Now, because it is bonded to two atoms on either side, it just considered as like, okay, two bond pairs are there, वैसे. This is the view that VSEPR takes. And VSEPR is also applicable to resonance structures because your basic geometry remains the same, right? Only the electrons are like delocalized and shifting among each other. So the basic skeleton or the geometry of the molecule will be the same, whatever VSEPR says. Clear on this? Key, what is the logic or the basic, the principle behind VSEPR?
Yes, ma'am.
All right. Now coming to what the shapes are going to be via CPR ka. So we'll be taking up, okay, another part. Now there are two types of electron pairs that can exist on an atom. Okay. So you can have either bond pairs or you can have lone pairs. Like for example, if you take water H2O, H2O का structure क्या होगा? O has 6 atoms and it has single bond with the hydrogen. So basically it has 2 bond pairs and it has 2 lone pairs of electrons. So whatever electrons are in the bonds are called bond pairs, and whatever electrons are just sitting alone on their own are called lone pairs. Okay. Now the order of repulsive interaction is दो लोन पेयर के बीच में मैक्सिमम रिपल्शन होगा compared to the repulsion between a lone pair and the bond pair compared to the repulsion between two bond pairs. Okay, so when you have conflicting nature ki acha you have both lone pairs and bond pairs, now I don't know how to assign the structure. Okay, अगर लोन पेयर दो लोन पेयर साइड साइड में है तो you're going to end up with one structure. अगर दूर दूर रखा है तो you're going to end up with another structure. So let's say you're confused कि what structure should I take. Maximum repulsion you should keep between lone pairs, followed by between lone pair and bond pair, followed by bond pair and bond pair. So the repulsive interaction between two bond pair of electrons is minimum. Okay, so lone pairs are localized on the central atom while the bond pairs are shared between atoms. That is why the lone pairs occupy more space compared to the bond pairs, because bond pairs are shared between two atoms, right? So they occupy less space. So the repulsive interaction is also going to be less between bond pairs as compared to the repulsive interaction for lone pairs. Hence, the order of repulsion is maximum between lone pairs than the bond pairs. And these repulsion result in increased deviations, and so the bond angles from the idealized shapes. So as
So,
we
ma'am,
look,
I have sorry,
yeah.
sorry.
Now I was saying, like as we take up each iteration of the structure, ये और अच्छे से like you'll be able to visualize and figure it out what this whole thing means. Okay. What's your question?
So the bond angles that are formed, would you
Yeah.
say it's because of lone pairs or like because of the bond pairs, like lone pair interaction or bond pair interaction?
It depends on whatever is existing there. So it's
Okay,
not solely because of the lone pair or the bond pair, it's because of the repulsive interactions between them. So agar lone pairs hai, to it's due to the repulsion between both the lone pairs. Agar एक lone pair hai and there are a couple of bond pairs, then it's because of the repulsive interaction between lone pair bond pair. And if you
okay.
have only bond pairs, then it's due to the repulsive interaction between the bond pairs, that way.
Because if you take H2O for an example, I mean, we've been told that it's because of the lone pairs that it pushes both the hydrogens down.
Absolutely. यहाँ पे because you have two lone pairs, in this case it's going to be due to the lone pairs. So again,
Okay, got it.
that is why this is the order of repulsion, right? So whatever is existing in the molecule, the most powerful repulsion will basically decide what the shape, what the bond angle is going to be. Okay. All right. So let's go back to this. One moment. Okay, so this is the shape. Actually, let me go over the chart first. How visible is it for you guys? Should I zoom in more or is this visible?
It's visible, man.
Visible? Okay. All right. So we are going to take up each all the permutations and combination possible with respect to your lone pairs and bond pairs, and then figure out what the shape should be. Okay. Now the base that you're gonna start with is, you want to maximize the repulsions between all the electron pairs, right? The only way to do that is to uh, basically get the most symmetrical structure possible, right? For example, okay, I'll take this up case by case only. So all right, this is the legend. Like, you have A, which is the central atom, X is whatever atom is bonded to A, and E stands for the lone pair on A. Okay, so if you have a generic formula AX, so that's just two atoms, you have A, you have X, there's only one bond atom, and they both are just attached to each other, right? So you don't have any interactions, repulsions, or anything at all, because there's only one bond pair. So the shape is going to be linear in any angle. If you have AX2, so that's A with two bond pairs of atoms, X on one side, X on the other side. This is the case that I just showed you. The maximum distance that can be attained between both the bond pairs of electrons, like to minimize the repulsion, is going to just arrange them on opposite ends of your central atom. That is why you end up with linear shape. Linear matlab line mein hai. That's all. So example is CO2 mein you will see this, like I just took up this thing. Hybridization, we'll discuss the valence bond theory, hybridization and all. Now what would be the bond angle when they are directly opposite to each other? ये दोनों bonds के बीच में angle 180 degrees. इसलिए yeah, इसलिए वो line बना रहा है. When you have AXE, मतलब you have A is an atom, X is only one X is bonded to it, so one bond pair, and E is one lone pair on A. So you have the two electrons here. This is lone pair. So in this case also, again, it's similar to your first case. The lone pair and the bond pair are going to be connected directly opposite to each other to maximize the distance between them. And so your shape is still going to be linear. Now, we're increasing the complexity. AX3. So there are no lone pairs at all. A is bonded to 3X atoms. Now, if you were to, again, imagine you had a inflatable, like a beach ball, and you had to stick chopsticks in it. Which is the most symmetrical shape, where, like, how can you stick those chopsticks in so that you end up with maximum symmetry? Like, what shape can you take up to ensure that symmetry is maximum?
Can you say that again, please?
So you have a central atom. Now you need to, like, this central atom needs to form a bond. Like, you have three of these X atoms. Imagine these are chopsticks that you need to poke in this central atom.
120.
So yeah, to maximize the symmetry, you are going to poke them such that the angle between them is all equal. Because if it is unequal, two of these bonds will be closer to each other, which means that wo repulse, like they'll start repelling each other. So in order to balance all of them, the most symmetrical shape is to have 120 degrees between all of these. Okay. And this is forming a triangle in the same plane. Like, if you imagine a piece of paper, you can take this molecule, put it on a piece of paper, and it's going to be flat. It's all falling on the same plane. So that is why this shape is called trigonal planar. So trigonal is tri, three sides, and it's a planar molecule. Like it's a flat molecule. Okay. So an example is AlBr3. So you can see that, even though it's aluminium, its covalent nature is high enough when it's bonding with bromine that this is the shape that it's taking up. So other examples of this type is BCl3 and BF3. Okay. Now, if you had AX2E, so basically two bond pairs, you have central atom A with two bond pairs and one single lone pair. Now logical shape, again it needs to be triangular, but the repulsion between lone pair and bond pair is going to be greater than the repulsion between each of these bond pairs. So will the bond angle still remain 120 in this case?
Shouldn't it be 117.5?
Yes.
Oh,
So in this case, the bond angle, now because lone pair has a tendency to repel more, यहाँ पे ये वाला bond angle increases, or this, you don't call this a bond angle because there is no bond, but the angle between the lone pair and this bond pair increases a little bit, which means that the angle between these two decreases a little bit. So if you had three bond pairs, it has to be perfect 120, but since you have one lone pair here, this particular bond angle decreases by a bit. So as Sid said, it's going to measure to somewhere around 117 or 117.5. So basically this particular bond angle is a little less than 120. So the reason is that the presence of this lone pair of electrons basically pushes these two bond pairs closer to each other. क्योंकि lone pair का repulsion is greater. Okay. And lone pair belongs to the central atom, right? So if you only look at the atoms, you have the central atom over here and the two X atoms are bonded over here, which is why the shape, अगर पूरा flat है, if there is no lone pair, तो पूरा flat है, it is linear, and this particular shape is called bent. So the molecular shape is bent. The electron geometry is trigonal planar because if you observe where the electrons are, they are still forming a triangle and they are in the same plane. So you have the lone pair over here and the two bond pairs over here. That is why molecular shape is bent, but the electron geometry is trigonal planar.
Ma'am, you said that the lone pair, sorry, lone pair bond pair repulsion. Sometimes, like the thing that you drew. So between the bond pairs, the angle sometimes decreases. However, the bond angle given here it's fixed. It says it's 120 only. So like,
Yeah, I'll have to, again, this one I just got it off of a Google page
okay,
because I wanted to show the shapes, but this is obviously not, it is not correct. Like all
so it will be
the,
like that minute thing, right? Or
yeah,
something.
yeah. So
Okay.
this angle is going to be, so it's not gonna reduce, it's not gonna become 90 all of a sudden. It's going to be slightly less than 120. It's gonna be like 117,
Minor
108.
fluctuations. Yeah,
Yeah.
got it.
Okay. And then, okay, so around A, we have three electron pairs. But instead of two bond pairs, if we have only one lone pair, one bond pair and two lone pair of electrons. So lone pair, anyway, only one bond pair. So the molecule shape is going to be linear because you just have two atoms A and X. But the electron geometry is still going to be trigonal planar. Then when you have four pairs of electrons, oh, this chart is not even complete anyway. So if you have 4 pairs of electrons, first case when all 4 of them are bond pairs, then it's going to be perfectly symmetrical. It's going to arrange itself in a tetrahedral shape, and the angle is going to be 109.5 degrees. Out of 4, if you have 3 bond pairs and 1 lone pair, like in ammonia, so the lone pair will occupy one position in the tetrahedron and the remaining 3 are going to be bond pairs. Now, what do you think will happen to the angle between the bond pairs? Will it be 109.5 degrees?
Compared to the tetrahedral above.
Yeah. So tetrahedron mein it's 109.5. But if
It
one
should
of
be
them is
slightly less than 109.5.
absolutely,
No,
yes.
yeah, because the lone pair will like push them down a little bit more than
Yes,
the original tetrahedral thing would, because there is no lone pair.
absolutely. So bond pair में जो repulsion है उससे ज़्यादा होगा lone pair bond pair में. So this lone pair is gonna push these bond pairs a little closer. So it's gonna be slightly less than 109.5 degrees. So the electron geometry, if you look at how the 4 pairs of electrons are arranged, is still going to be tetrahedral. But if you look at the molecule alone, so you have central atom here and you have the 3 atoms over here, the bonded atoms. So what kind of shape do you observe here? So what does it look like? So if I were to draw a rough shape, 3 इधर है,
Pyramid.
हाँ पिरामिड जैसे है ना.
But this is if I don't consider lone pairs.
हाँ, because
Should we consider lone pairs?
no. So molecular
Okay.
shape में the lone pair belongs to this atom only. It's not occupying any extra shape here. So molecule geometry में you don't consider the lone pairs. Electron geometry में you are considering अच्छा where are all the electrons, तो इसलिए you will say it's this thing. Okay. Now because it is pyramidal in shape, but you only have like 3 uh, bonds over here. It's like a pyramid with 3 legs. That's why you call it trigonal pyramid, or you can say simply pyramid also. ठीक है. Then okay, I'll just stop it till here so that because I want to show you guys the simulations of this. Yeah, water nahi. So the first one, VSEPR में ammonia. So ammonia में how many bond pairs, how many lone pairs are there?
1 lone pair, 3 bond pairs.
1 lone pair, 3 bond pairs. So you can see that here the electron geometry is going to be tetrahedral because there are 4 pairs of electrons. But because there are 3 bond pairs, so nitrogen is connected to 3 hydrogens, you can see that it's taking on a pyramidal shape. So this is what it's going to look like. And you can see that the bond angle, original tetrahedron mein it was 109.5 degrees, but
It's less.
because यहाँ पे lone pair है that's pushing all the electrons down, this has become 106.7 degrees, less than your normal tetrahedron का angle. Okay. So this particular shape is called trigonal pyramid because it looks like a pyramid, right? You have a pointed top and then niche it's like spreading out in like different directions. Now because it is spreading out in 3 different directions, it has 3 faces. That is why it is called trigonal pyramid. So this is like the 3D shape you can see. That's what it's like. Okay. Uh, then what other can we discuss? Methane. So this is another atom with four pairs of electrons around the central atom, but all four of them are bond pairs. So it is a perfect tetrahedron, and because all four of them are equivalent bond pairs ही है, तो tetrahedron का angle bond angle is 109.5 degrees. So this is what a tetrahedron looks like. So you have one on top and you have three on the bottom. So if I rotate it such that any one particular this thing is on top, it's still gonna look the same. ठीक है. So you can see it here 2D में it's drawn. So C occupies central position, and you get that pyramid if you join the four ends. Like if you join these three, नीचे triangular base है और ऊपर एक pointed आएगा. So this is like a perfect tetrahedron, symmetrical. Okay. Then बाकी सारे, okay, these we have not discussed yet. बाकी सारे again we have seen linear only. Trigonal में we don't have any trigonal का examples here, but basically that's like a 2D triangle ही form करेगा. So that's not there. So 4 नहीं 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 ठीक है. Cool. So remaining VSCPR I will discuss in the next class because it's already 5 o'clock. अभी के लिए I'll send you guys the questions. But have you guys gotten the logic of
Related to
VSCPR?
Yes.
Hmm?
You will be sending questions today related to VSCPR or
No, I won't be
the
doing
thing that we did
VSCPR
before?
because complete नहीं किया.
Okay.
So remaining concepts पे questions I'll send. Okay.
Okay, ma'am.
All right. So, but at least have you guys gotten an idea of what VSCPR is about? थोड़ा better idea मिला? Because other than that, we'll just be discussing different cases कि अगर
Yes.
5 bond pairs है तो क्या, 4 bond pairs, 1 lone pair है तो कैसे होगा? Like we'll just be discussing all these different cases. That's it. Okay. Cool. All right. So shall I end it now?